Hi, theory students. In this second part of the chapter, we'll be looking at how to put to use what we had learned about set classes in different musical situations. In this part, we'll be looking at the three-note sets or trichords and where they occur in the kinds of scales that we've been studying. We'll also look at the idea of complementary sets, that is to say, sets that when they're combined will give you all 12 pitches. And we'll also be looking at how to use interval class vectors in interesting and informative ways. First of all, there are 12 different trichord set classes, and you can see why I arranged them in 4 different columns like this. The first column are all the ones that have semitones in them, and the index numbers 3-1, 3-2, 3-3, 3-4, and 3-5. Those are the Alan Forte classifications for each of these prime forms. The second column begins with a whole tone, so O2-4, O2-5, O2-6, O2-7. The third column begins with a minor third, O3-6, that's our diminished triad, O3-7, that's our minor triad, or actually, if we invert it and go that way, that's our major triad as well. And the last column is the augmented triad, O4-8. There's an easy way to remember the index numbers. If it has a semitone, then the index number is 1 less than the last member of the prime form. So here's a 2, and this is set class 3-1. Here's a 3, set class 3-2, etc., all the way across. In column 2, if you add up all the numbers, you get the index number 6. Add these up, you get the index number 7, etc. That's also true for the last column, where 4 and 8 equal 12. This column, the diminished and minor triads are different. You may just have to remember those. Those are the ones that are left over. 310 is a diminished triad. 311 is our ordinary major or minor triads. Here's where we find them in the scales that we use, and there are good examples in the book. So O2-4 could be found as part of a whole tone scale. O2-6 or O4-8, our augmented triad, are all trichords that we find in whole tone scales. In pentatonic scales, we may find O2-5 or O2-7 or even O3-7, as well as O2-4, which we also find in the whole tone scale as well. Our octatonic scale it might be easier to see this if I write out the pitches. And now here you could see O1-3 as part of that scale, O1-4, O1-6, and O3-6. And those are all part of the octatonic scale. The fully chromatic scale also uses O1-2 and O1-5 And of course, the fully chromatic scale, you could get any trichord out of it because the fully chromatic scale has all 12 pitches. So here's a way to read the set class tables. Turn in your book to Appendix 5 so you could see what we're talking about. Appendix 5 starts on page A, as in Appendix 83. Complementary sets are those that can combine to form the aggregate. The table is set up so that the complements have numbers that add to 12, and they have the same index number. For example, set class 428 is our fully diminished seventh chord. The prime form is 0, 3, 6, 9. Set class 828 is our octatonic scale. Now, you might be saying, how could these be complements if there's a 0 in each of these, a 3 in each, a 6 in each, and a 9 in each? We'll never get all 12 pitches by combining these. The trick is that if I take a 428 and I transpose it by 2, there we go. The transposed form of the 428 plus the octatonic prime form, and you'll get all 12 pitches, or the aggregate. The important thing to remember here is that every pair of sets, the 4-note and the 8-note sets that have the same index number, are complements of each other because there is some transposition or transposition and inversion of one set that will give all the notes that are not in the other set. That's what we mean by a complement. You could picture this around the clock. So for example, if I take set class 310, where the prime form is 0, 3, and 6, there are 9 pitches remaining. Here they are. And imagine if I start on 11 and start counting the intervals. We'll start with 0, and the next note down is 1 away, and another 1, another 1, another 1. So imagine 0, 1, 2, 3, 4. We skip this 1, and now 6, 7. We skip that 1, 9, and 10. I just wrote the prime form to set class 9-10. So we noted that the cardinality or first numbers add up to 12, and the index numbers are the same for complementary sets. Now about interval class vectors. One pair of tetrachords shares the same interval class vectors. 4z17 and 4z29 each have the interval class vector of all ones. We call these two the all-interval tetrachords because each interval is represented. Every other tetrachord has at least one 0 somewhere here in the IC vector. We call these Z-related because they have the same interval class vector, but you cannot transpose or invert this set class and that set class, so they belong to different set classes. Okay, beg your pardon. That's not 17, but that's 15. So 4Z15 is 0146, and 4Z29 is 0137. You could probably see that, try as you might, you cannot transpose and invert this to end up with that. So those are different set classes, even though they share the same interval class vector. There are also 3 pairs of Z-related pentachords and 15 pairs of Z-related hexachords. Now here's an interesting fact. For hexachords, a set's complement is the Z-related pairing if there is one, or itself if there's not. For example, a trivial case, set class 6-1. If you transpose this set by 6, then it forms its own complement. It's not so trivial that the Z-related pairs, you could tell which ones are Z-related because they'll have the same IC vector, are complements of each other but not of themselves. And now finally, the common tone theorem. The interval class vector can predict how many common tones will recur if a set is transposed by a certain interval. So let's take as an example set class 4-3. Prime form is 0134. There's the interval class vector, 2 of interval class 1, a single case of interval class 2, 2 cases of interval class 3, 1 case of IC4, and no IC5s or tritones. If we transpose this prime form by a minor second, IC1, we get 1, 2, 4, and 5, which contains 2 different pitches, 1 and 4, that were in the original set. And that was predicted because there's a number 2 here. That means when we transpose by this interval class, we get that many pitches recurring. Now this theorem predicts that if we transpose by interval class 5, a perfect fourth or perfect fifth, we'll get none of these pitches recurring. So let's try it. From 0 to 5, from 1 to 6, from 3 to 8, from 4 to 9. Or going the other way, from 0 to 7, from 1 to 8, from 3 to 10, and from 4 to 11. That's transposing up by 7 instead of 5. And note that each of these 4 pitches are not contained here, and each of these 4 are not contained here either. The 0 told us when we transposed by that amount, we would get 4 new pitches. None of them would recur. One catch here, which is not present in this particular example, is that these first 5 spots will predict how many pitches will recur if I transpose by each of these. What it doesn't show is that in IC6, the tritone, this happens to be 0, but if IC6 were 1, that would give me 2 common tones when I transpose by a tritone. If this placeholder were 2, I would get 4 pitches. If it were 3, I would get 6. And that's because tritones are symmetric around the clock. So if you think about it, if you have a 1 and a 7, so now there's at least one IC6 here between these 2 pitches. If I transpose by a tritone, 1 becomes 7, and 7 becomes 1. They just swap places. So as I said, for every one number in the vector for IC6, you get 2 common tones recurring. And finally, the idea of modes of limited transposition. The composer Olivier Messiaen discovered scales that, when transposed by a certain interval, generated all the same pitches. We already learned that the whole tone scale has only 2 pitch collections, and the octatonic scale has only 3. These are only a few of the possible ones. Messiaen worked with these modes of limited transposition and used them in his pieces, and there's a good example in our textbook. There are other sets that won't generate all the same pitches when you transpose them, but they will generate all the same pitches when you invert them. The set we looked at before, 0, 1, 3, 4, because it's symmetric forwards and backwards, we can find at least one transposition that will give us the exact same pitches when we invert. We'll be dealing with more of this in class, but that's all for today.